So welcome you back to today's module. So last time we were discussing the asymptotic distribution approach to compare two or more estimators. And our whole discussion was centered around the realization that for many reasonable estimators, their asymptotic distribution after suitable normalization tends to normal. So their asymptotic distribution is normal after certain normalization and centering. Then we said that if that is the case, then asymptotic variance makes sense to compare different estimators, or one can compare different estimators in terms of asymptotic variance of the limiting distribution. Of course, for all such estimators, you would expect that kn times delta n minus g theta goes to normal with mean 0 and certain variance tau square theta. So this suggests that what I should try to do is, if I have two estimators which after suitable normalization tend to normal with mean 0 and certain variance, I should first see for which the convergence rate is much higher. That means the corresponding normalization factor kn or mn, for which 1 upon kn or 1 upon mn is going to 0 at a much faster rate, or kn is going to infinity at a much faster rate. Now, if for the two sequence of estimators that rate of convergence is same, then I can look at the one for which the asymptotic variance is smaller. So first let me define the definition of consistent and asymptotically normal estimators, because this method which we talked about gives you a way to compare those estimators which are consistent as well as asymptotically normal. So their asymptotic distribution is same, right? It may not be appropriate to compare two sequence of estimators for which asymptotic distribution does not belong to the same family. For example, for one, suppose it belongs to normal, for second it belongs to exponential. Then comparing such estimators through their asymptotic variance may not be a reasonable thing, because the role of the distribution also comes into the picture. But wherever the asymptotic distribution is same and it is a normal in many situations, so it makes sense to talk about comparing consistent and asymptotically normal estimators. But for that, first let me give a definition of a CAN estimators. Consistent and asymptotically normal, will commonly denoted by CAN estimators. So what are those estimators? I have a sequence Kn. So there exists a sequence Kn such that Kn goes to infinity as n goes to infinity. And what you have is Kn times delta n minus g theta goes in distribution to some random variable, to normal distribution with mean 0 and variance tau square theta, where tau theta is positive for everything. Now, such estimators are called CAN and asymptotically normal. Now, clearly, such estimators are asymptotically normal. Why they are consistent? Why star implies consistency? Because delta n minus g theta, to show that it converges in probability to 0, what I do is I can write down this as 1 upon kn into kn times delta n minus g theta. Now this goes in probability to, this goes in distribution to y, which is normal 0 tau square theta. And 1 upon kn is going to 0, because kn is going to infinity. So kn going to infinity is important. So this product, that is y, will go in probability to 0. So that shows that it is consistent. So any estimator for which this happens, for any sequence kn, for some sequence kn going to infinity, such estimators are called consistent and asymptotically normal. So wherever I use x bar as estimator, x bar is consistent and asymptotically normal for the population mean. Because of the central limit theorem, because of my central limit theorem, I know that root n x bar minus theta goes in distribution to normal 0, 1, or normal 0 sigma square. So that means CAN estimators can be compared. So comparison of CAN estimators can be thought of it can be done in two directions. The first one is, certainly I should prefer for which the error rate goes to 0 at much faster rate. So prefer the one for which delta n minus g theta goes to 0 at a faster rate. For example, if for some the normalizing theory is root n, and for the other the normalizing thing over here n, you prefer for which the normalizing thing is root n. If error rate is same, prefer the one having smaller asymptotic variance. So a straightforward method to compare two different sequences of estimators. So now the question is, I need to find out what is the asymptotic variance in certain situations. Now if you recall your last course, you talked about Cramer-Rao lower bound. Cramer-Rao lower bound gives you the lower bound on the variance of all estimators, all unbiased estimators. Now here, asymptotically, you would expect all reasonable estimators to be unbiased. So it looks like Cramer-Rao bound could be of some use over here. So let us try to see what is the Cramer-Rao bound so that you can use it to get asymptotically efficient estimators. So Rao-Cramer bound. Of course, one may also call it as a Cramer-Rao bound. I'm using it Rao-Cramer bound. So what you have is x1, x2, xn, IID with PDF or PMF f theta, where theta belongs to capital theta. Let me put, which is subset of R, basically, not whole R. So if you recall the regularity conditions of a Cramer-Rao bound, they involved interchange of integral and derivative sign, and then you had seen all such conditions are satisfied in the exponential families. So this Cramer-Rao lower bound can be blindly applied to all exponential families. So suppose that, so what are the assumptions? I required theta is an open interval. So I am doing it for one parameter case, and the density in the real line. B, support of x1 does not depend on theta, which happens in the exponential family. Then I assume that because if you recall, Rao-Cramer bound requires Fisher information, which is second derivative with respect to the density function. So I'll have to assume that the second derivative with respect to the theta of the density function exists. For every theta belonging to theta, f theta is twice differentiable with respect to theta with continuous second derivative. Second thing is integral over f theta x d mu. Now d mu could be counting measure in the discrete case, in which case this integral would be summation, and Lebesgue measure in the discrete in the continuous case. Can be twice differentiated. First you know that the value of this integral is 0. Sorry, the value of this integral is 1. So when I say it can be twice differentiated, the second derivative has to be 0. But if second derivative has to be 0, I am saying that here the derivative, second derivative would be sitting outside. I can take it inside the integral sign. Can be twice differentiated under the integral sign. Now if that happens, if you recall, then it becomes del by del theta log of f theta x1. And expected value of minus which is same as expected value of, just recall your first course, which is same as I of theta, or you call it as a small I theta. Capital I theta is, I think, the information in the whole sample. Then I assume that second derivative is bounded. So I'm saying that for every parametric point theta naught, I can find a neighborhood around theta naught, which is equivalent to check that del x is a c greater than 0, such that the second partial derivative is uniformly bounded f theta x. So let me put log of is always bounded uniformly by mx for every theta in neighborhood of theta naught, where this mx is integrable. So that means expected value of m of x1 is finite. So this would be for every x belonging to A. Of course, A means the set collection of all those x belonging to chi, such that f theta x, or x belonging to R, such that f theta x is positive. So essentially, A is the support of the random variable x. Let delta n be any estimator such that root n delta n minus g theta goes in distribution to normal 0 v theta. I am not going to prove it. I will give you idea of the proof. So under these conditions, what does your Kramer-Rao lower bound says? That variance of delta n would be greater than or equal to g prime theta whole square by n times I theta. That is what this says. Now I give this result in terms of a limiting variance, then v theta. So this asymptotic variance which you are getting is always greater than or equal to g prime theta by I theta. Small I theta, you can put it. For all theta belonging to capital theta. Now, what may happen is it may happen almost everywhere. So that means it will happen for every theta belonging to theta, except on a set of Lebesgue measure 0. So that means the point where it does not hold, or the set where it does not hold, cannot contain any interval. So it is, that means this holds for every theta belonging to theta except on a set of Lebesgue measure 0. That means the set where it does not hold, that cannot contain any interval. What I do is I give you the idea of the proof, or the heuristic argument why such a thing would hold. Of course, one can prove it. The proof is technical, and that's the reason why I don't want to go about it. But I can give you the heuristics behind this result. Let us look at the Rao-Kramer bound, which you did in your last course. What does the Rao-Kramer bound says? It says if the expected value of delta n is g theta for every theta belonging to capital theta. So delta n is any estimator for which expected delta n is g theta for every theta, and the regularity conditions of last theorem are satisfied, then variance of delta n is always greater than or equal to g prime theta by n times. So now if root n delta n minus g theta goes in distribution to normal 0 v theta, then you know that limit infimum of variance of root n times delta n minus g theta would always be greater than or equal to. So limiting risk is always greater than or equal to asymptotic variance. So this will always be greater than or equal to v theta. So what does that say? Now this quantity from here is same as variance of delta n. So what do you get? 1 and 2. So you get last result using 1 and 2, provided. So last result follows from 1 plus 2. Because if there is an equality over here, then what you get is limit of variance of root n delta n minus g theta, which is limit n going to infinity variance of delta n, root n delta n would come over here, would be greater than or equal to g prime theta by I theta. So provided limiting risk is same as the asymptotic variance. So that means provided limit of variance of root n delta n minus g theta is same as v theta. So that would be in many scenarios or many situations. So this in a sense gives you, because as I have said, this condition would hold in a lot of situations. There would be few situations where it doesn't hold. So in all such situations with this holds, the proof just follows from 1 and 2. Because this is nothing but root n delta n. So this says limit of variance of root n delta n, which is same as v theta, is always greater than or equal to g prime theta whole square by I theta. The last result follows from Kramer-Rao-Low bound. So from last result, I say that if certain regularity condition hold, then asymptotic variance is always greater than or equal to this quantity. So this gives me idea to define locally, to define asymptotically efficient estimators. So I'll call an estimator delta n to be asymptotically efficient if there exists a sequence kn such that kn times delta n minus g theta goes in distribution to normal 0 v theta, and v theta is exactly same as that Cramer-Rawle over bound over here, g prime theta whole square by I theta. So this would be n times I theta. Yeah. So let me give this definition. So delta n is a sequence of estimators. This is said to be asymptotically efficient for estimating g theta if the following conditions are satisfied. So first is there exists a sequence kn of real numbers such that kn goes to infinity, and and kn times delta n minus g theta goes in distribution to normal 0 tau square theta for some tau square theta greater than 0 for every theta. Or in other words, I say that delta n is asymptotically efficient. The first condition it is can, because this is a condition for can. Second thing is, let me not write down this tau square theta, let me write down this as v theta. And second thing is, whatever is the limiting or asymptotic variance that attains the Cramer-Rawle bound. So v theta is same as g prime theta whole square by I theta. Now we got motivated to give this definition based on this result. But this result holds under certain regularity conditions. So this suggests that in many situations, although the asymptotically efficient estimator exists, but there is no guarantee that asymptotically efficient estimator exists. So if you can find a situation where such a thing holds, of course, for which you will have to ensure that those regularity conditions are satisfied, I can outrightly pick up the most efficient estimator in asymptotic sense, the way you are doing it for the Cramer-Rawle bound. Wherever you could find an estimator which attains the Cramer-Rawle bound and those regularity conditions are satisfied, which always happen in the exponential family, so you always say that I have got the uniformly minimum variance in my estimator. So similar thing can be said over here, and then for sure you are guaranteed about the satisfying of those regularity conditions in exponential families. So Poisson, gamma, normal, so all the distributions, nice distributions which you can think of, there this result is applicable. Now note that this says that this would be satisfied at every theta except on a set of Lebesgue measure 0. So that means there could be points where this is not satisfied, although their Lebesgue measure would be 0, or although the set where it does not hold cannot contain any interval. So there could be situations where, although it is satisfied for every theta, almost everywhere, but there could be some thetas where it does not hold. So let me write down this as a remark. So there exist estimators delta n and a sequence kn such that kn goes to infinity, kn times delta n minus g theta goes in distribution to normal 0 v theta. V theta, but v theta is greater than or equal to g prime theta whole square by I theta, which by last result holds almost everywhere, but there could be some thetas where it doesn't hold. So, but this getting violated. At some thetas. Of course, from the last result, you know that if those regularity conditions are satisfied, then the set of all those thetas where this would get violated, that has Lebesgue measure 0. Or in other words, they are almost negligible. Negligible in the sense that set is negligible where this gets violated. Or in other words, that set cannot contain any interval. So we'll see that next time, but let me tell you the points where it gets violated are called points of superefficiency. So such points where this gets violated, which although has a Lebesgue measure 0, are called points of superefficiency. So for theoretical interest, I'll give you one example where although this is satisfied for every theta, but there are some thetas where it will not be satisfied. So that's all for today. So tomorrow I'll begin with an example of a situation where this gets violated at some thetas. That means I'll try to look for an example where I can find points of superefficiency. So see you in the next module. Thank you very much.